Okay, we're going to talk about fundamental subspaces. The problem we're going to try to solve here, we're going to look at operator equations of the form y equals a operating on x. Given y with knowledge of a, can we solve for and find x? Okay, so these are general operator equations. The setup is as follows. So, A is going to map H1 to H2, and H1 and H2 are Hilbert spaces. We also have to assume that, that A is bounded. Okay, so it's a continuous operator, or the norm of the operator is equal to, or is less than infinity. And then we also have an adjoint. Okay, so remember the operator operates in this direction from H1 to H2, and then the adjoint is going to operate in the opposite direction from H2 to H1. And I'm going to use this little diagram to basically illustrate what's happening with these operator equations. I call this my telephone, telephone pole diagram, because we represent the Hilbert space H1 as this telephone pole, and the Hilbert space H2 is this telephone pole. And what we're trying to represent here is that, A is going to take all of H1 and map it down onto the range space of A. Okay, so the range space of A, of course, is in H2, and so all of H1 gets mapped onto the range space of A. And then with A star takes all of H2 and maps it over here to the range space of A star. Now it turns out that in H2, the range space of A is actually, if you look at H2, it can be completely decomposed into the range space of A and the null space of A star. This little symbol here represents, orthogonal, the orthogonal sum. And what we mean here is that H2 is exactly equal to the range space of A, orthogonal sum, with the null space of A star. Okay, so in other words, these spaces are disjoint, and they're also orthogonal to each other. So in other words, range space of A is orthogonal to the null space of A star, and that means that if YR is in the range space of A and YN is in the null space of A star, that the inner product of Y and YN is going to be equal to 0, or YR with YN is going to be equal to 0. It also says this orthogonal decomposition means that if we have any Y in H2, that implies that Y can be written as a unique decomposition of something in the range space of A plus something in the null space of A star. Okay, so this is that's what it means to write that H2 is equal to the orthogonal decomposition of the range space of A and the null space of A star. Similarly, we can say that H1 is the orthogonal decomposition of the range space of A star and the null space of A. Okay, so the straight line here, what we're trying to represent here is that it turns out that the dimension of the range space of A is going to be exactly equal to the dimension of the range space of A star. So most of this lecture is going to be proving all of these statements, by the way. I'm just telling you the result at the end. And so we're going to go about proving that the dimensions of these range spaces are equal and that H1 and H2 can be decomposed as I'm telling you. Okay, so this is kind of a summary of the things that we're about to show. Again, as a restatement, H1 is going to be the null space of A, orthogonal decomposition with the range space of A star. H2 is going to be the orthogonal decomposition, is equal to the orthogonal decomposition of the null space of A star and the range space of A. Another way to say this is if I look at the dimension of H1 is going to be the dimension of the null space of A plus the dimension of the range space of A star, and the dimension of H2 is actually equal to the dimension of the null space of A star plus the dimension of the range space of A. And then finally, we're going to show this result, that the dimension of the range space of A is equal to the dimension of the range space of A star. So before proving this, let's look at what what this looks like for the matrix case. So if we have a matrix A that takes complex n space to complex m space, in other words, if we were to write y equals ax, this guy is in complex n, and it maps over to something in complex m, and A is an m by n matrix. Of course, x would be an n by 1 matrix, so the dimensions are compatible, and that produces an m by 1 matrix. Okay, so in this case, again, we have the fact that the range space of the matrix is can be, in other words, the Cm can be decomposed as the orthogonal decomposition of the range space of the matrix A and the null space of AH. And because, of course, the adjoint of a matrix is the Hermitian. And similarly, Cn can be represented as an orthogonal decomposition of the range space of AH and the null space of A. And the dimension of the two range spaces are equal to the same. We haven't defined rank yet, but in fact, this will imply that the rank of A is equal to the rank of AH. And we'll see that here in a little bit. Okay, so we're going to prove all of these statements, and we start by showing this theorem from Moon theorem 4.5. So again, we're going to let A map from H1 to H2. It's going to be bounded, and H1 and H2 are Hilbert spaces. And we also have to assume that these range spaces, the range space of A and the range space of A star, these range spaces are closed. Okay, in this case, we can make two statements. First of all, that the space that is orthogonal to the range space of A is actually equal to the null space of A star. So if we go back to this picture, we're going to say that the space that is orthogonal to the range space of A is actually equal to the null space of A star. So this means, in fact, because H2 is going to be equal to, we know that H2 is equal to the range space of A plus the, so I guess I could write it here. We know that we know that H2 is equal to the range space of A, orthogonal decomposition with the space that is orthogonal to the range space of A. So this would be, kind of a tautology. So it's H2 can be decomposed in terms of this is inside of H2 and then everything else. So what we're going to show is that everything else is equal to the null space of A. And similarly, we can say that the space that is orthogonal to the range space of A star is actually equal to the null space of A. So it turns out that the proof of 1 and 2 are basically the same. It's just after we've proved 1, every time we mention A, we can say that we use H star, and every time we mention A star, we use A. And so we will, we're only going to prove item 1 here. So to prove item 1, to show that the space that is orthogonal to the range space of A is equal to the null space of A star, we need to show two things. Number one, we need to show that the null, this is a typo, that the null space of A star is contained inside of the range space, or inside of the space that is orthogonal to the range space of A, and the space that is orthogonal to the range space of A is contained in the null space of A star. So let's first of all show this guy, okay? So to show that this space, the null space of A star, is contained in this space, the space that is orthogonal to the range space of A, we need to show that if we pick something arbitrary inside of here, that it's also inside of there. So let's go ahead and select Y to be any, and so it's any element of the null space of A star. And then let's pick any Y hat that's in the range space of A. And if we can show that Y and Y hat are orthogonal to each other, then we'll know that, Y has to be inside of the space that is orthogonal to the range space of A. And therefore, the null space of A is included there since we've picked any Y. All right, now, if Y hat is in the range space of A, what does that mean? That means that there's some X hat in H1. Remember, A goes from H1 to H2. So if there's a Y hat in the range space of A, then there has to be an X hat in H1 so that Y hat equals AX hat. That's what it means for Y hat to be in the range space, that there's something over here in H1 that maps to Y hat. Okay, so now let's look at the inner product of Y hat with Y. We know that Y hat is some AX hat, or A times some X hat. That's inner product with Y. And now we use the property of the adjoint. So remember, the important property of the adjoint is, in fact, for any X and Y, the inner product of AX with Y has to be equal to the inner product of X with A star Y. So this is the definition of A star. Okay, so by definition, we get this line here. So X hat, A star Y. Now, what do we know about Y? Well, it's in the null space of A star. So A star times Y, that has to be, this vector here, that's equal to 0. And so we get that X hat is inner product with 0. Of course, you inner product anything with 0 and you get 0. So that implies that Y hat and Y are, in fact, orthogonal to each other. And therefore, Y is contained in the space that is orthogonal to the range space of A. So therefore, we've shown that the null space of A star is contained in the range space of, or the space that is orthogonal to the range space of A. Okay, so now we need to show the opposite direction, that the space that is orthogonal to the range space of A is actually contained in the null space of A star. So let's do this. It's the same thing. We're going to pick an arbitrary vector in here and show that it's in fact in the null space of A star. So we pick any Y that's in the space that is orthogonal to the range space of A. Okay, and so that means now for any X hat in H1, we can find something that's in the range space of A. We just map over through A, and Y hat has to be in the range space of A. So now if we take the inner product of Y hat and Y, we get Y hat is going to be AX hat is equal to Y. And we know that these things are orthogonal to each other, right? Because Y is in the range space of A, or Y hat is in the range space of A, and Y is in the space that's orthogonal to that. So we know that this inner product now is equal to 0. By definition of the adjoint, we have that X hat A star Y has to equal 0. And since this is true, and it's true for every X hat in H1, not just 0, but for all the other ones, the only way this can be true for every X hat is if A star, if this piece is actually equal to 0, which means that Y is in the null space of A. So we have that the space that is orthogonal to the range space of A is contained in the null space of A star. And so if we go back here, we've shown, this item because we showed both that the null space of A star is contained in the space that's orthogonal to the range space of A, and the space that's orthogonal to the range space of A is contained in the null space of A star. And again, if we were to, reverse the arguments, we show the other property as well. Okay, so now we can say, because for any Hilbert space and any closed subspace, we had this theorem, 2.10, that we can always write the Hilbert space as a closed subspace and an orthogonal sum with the space that's orthogonal to that closed subspace. So theorem 4.5 then, what we just showed is that H1 can be written as a unique orthogonal decomposition in terms of the range space of A star and the null space of A. H2 can be written in terms of a unique orthogonal decomposition of the range space of A and the null space of A star. This also implies the statement about dimensions because, of course, the dimension of this space is the number of linearly independent vectors. And so H1, we have a certain number of linearly independent vectors. And so then we have, the dimension here will be the number of linearly independent vectors that span the range space of A star. And we have the number of linearly independent vectors that span the null space of A. Since they're orthogonal to each other, we can't have any non-zero element here that's also there. So the number, the dimension of H1 has to be exactly the dimension of this guy plus the dimension of that guy. Okay, so we've shown at least this dimensional argument. Okay, so the last thing we need to show is that the dimension of the two range spaces are exactly the same. And to do that, we're going to have an intermediate result, which is actually, important in and of itself. So I'm going to just redraw this telephone pole diagram for a minute. This is H1, this is H2, and A goes in this direction to the range space. So this is the range space of A, and H2 comes over here, and this is the range space of A star. Okay, so if you look at this operator, so A takes elements in H1, maps it into H2, and A star takes elements in H2, maps it into A1. Now let's look at this operator A star. What does this do? Well, it's going to map. You're going to put on the right hand side here a y, and y has to come from H2 because A star operates on H2, and it's going to produce will produce something in H1, and then A maps it right back to H2. So A star maps H2 onto itself, H2. So in other words, A star goes, it starts in H2, goes over to H1, and comes back. That would be A star. And this first statement says that if we look at the range space of A, that's going to be exactly the same as if we started in H2, mapped over to H1, and came back to H2. So this thing has to be equal to the range space of A star. And similarly, if we were to, look at what this operator A star A is, so A starts in H1 and maps something to H2, then A star goes H2 back to H1. So in fact, going H1 back onto itself would be A star A, okay? And it turns out that the range space of A star is actually equal to the range space of A star A. Okay, so we're going to show this, and we're only going to show item 1 because item 2 is the same. Again, we replace A with A star and A star with A, and we get the same result. So we're going to show item 1, just following the same logic. We're going to show that the range space of A is a subset of the range space of A star, and the range space, and then the range space of A star is a subset of range space of A. Therefore, the two of them have to be the same. Any element in range space of A is also an element in the range space of A star, and any element that's in the range space of A star is also in the range space of A. Therefore, the two are equivalent. Okay, so how do we prove item 1? So again, item 1 is that the range space of A we're trying to show that the range space of A is contained in the range space of A star. And to show that, we're going to pick an arbitrary element. So the first thing we do is we're going to pick an arbitrary element of the range space of A. See here? And then we're going to show that it's actually in the range space of A star. Okay, so if y is an arbitrary element in the range space of A, that means there's some x in H1 so that y is equal to ax. That's what it means for y to be in the range space of A. There's some x that maps over to y. Now, since H1 is the orthogonal decomposition of the range space of A star with the null space of A, we can write that particular x that mapped over to y as xn plus xr. This is a unique orthogonal decomposition, and we know that xr is going to be in the range space of A star, and xn is in the null space of A. That's what it means for H1 to be written in this way. Okay, so now we know that xr is in the range space of A star. What does that mean? Well, it means that there's an element y hat in H2, so that y hat maps through A star to the range space of A star, to xr, which is in the range space of A star. Okay, so we can then write, y is going to be A operating on x. We've decomposed x in terms of xn plus xr, and xn is contained in the null space of A. So when A operates on xn, we get 0. And so this is just A operating on xr. I suppose I'm missing a statement here. This should be, A operating on xr. And we know that xr is equal to A star y, so that's A star y hat. Sorry, xr is equal to A star y hat. So y then is A star y hat, which means that y is in fact in the range space of A star. So we've shown that, anything that's in the range space of A is also in the range space of A star. Now to go back the other direction, we pick an arbitrary, so for the second one, we want to show that the range space of A star is contained in the range space of A. So we're going to pick an arbitrary element in the range space of A star. So let y be an element of the range space of A star, and we want to show that it's in the range space of A. So what does it mean for it to be in the range space of A star? Remember, A star maps from H2 to H2, so that means that there's some y hat in H2 so that y is equal to A star y hat. That's what it means for y to be in the range space of A star. Okay, but A star y hat, you can think of that as, see, this guy has to be in H1. So you can think of this equation here as just y equals ax hat, where x hat is in H1. Okay, because, and it's also in the range space of A star, but its range space of A star is inside of x1. So that means that there's some x hat that gets you to y. So y has to be in the range space, or through A. So y has to be in the range space of A. Therefore, anything that is in the range space of A star is also in the range space of A. All right, so we've shown this theorem, that the range space of A is equal to the range space of A star, and by a similar argument, the range space of A star is equal to the range space of A star A. All right, so now we're ready to show this mean result, that the dimension of the range space of A is equal to the dimension of the range space of A star. And we're going to follow similar logic. We're going to show that the dimension of the range space of A is less than or equal to the dimension of the range space of A star. And we're going to show that the dimension of the range space of A star is less than or equal to the dimension of the range space of A. And it turns out we really only need to show item A, because we could just, in our argument, we'll be able to replace A with A star and A star with A and get item B. So we're going to show item A. The dimension of the range space of A is less than or equal to the dimension of the range space of A star. Okay, and let's just think about the logic of how we're going to do that. First of all, what is the dimension of the range space of A? It's the number of linearly independent vectors that span the range space of A. So what we're going to do is we'll start out with linearly independent vectors that span the range space of A, and we'll show that in fact they're linearly independent over here in the range space of A star. So they may not span all of it, but they are linearly independent, and so anything that spans the range space of A star is going to have to include at least those vectors. So the dimensions will be less than or equal. Okay, so let's do it. Let P be these sets of vectors, P1, P2, and it's a Hamel basis for the range space of A. So in other words, they're linearly independent, or any finite subset is linearly independent. That's what it means to be a Hamel basis. We have complete bases and Hamel bases. The Hamel basis is what gives us the dimension of the space. Okay, so the dimension of the range space of A is the cardinality of P. It's how many elements are inside of P. Okay, so let Pi be one of these guys. And it, of course, it forms a basis for the range space of A, so it's in the range space of A. And that means there's some Q hat in H1 that maps over to that Pi. Okay, again, that's what it means to be in the range space of A. So there's some Q hat. Now, H1 is an orthogonal decomposition of the range space of A star in the null space of A. That means that Q hat here, this Qi hat, can be decomposed into something that's in the null space of A and something that's in the range space of A star. So Qin is in the null space, and then this Qi without the hat is in the range space of A star. And since A operated on Qi hat, A will operate on Qi in the null space of A, gives you a 0. We can just write Pi is equal to A Qi, and Qi is in the range space of A star. So now we do that for each of these basis vectors in the range space of A, and we get a set of vectors that are all in the range space of A star. Now what we need to show is that these vectors are in fact linearly independent when these vectors are linearly independent, and that will give us that the dimension of the range space of A has to be less than the dimension of the range space of A star. Okay, so again, we're going to try to show that these guys are linearly independent when Q is linearly independent, when P is linearly independent. Okay, so P is a Hamel basis. That means all finite what's the definition? All finite subsets of P are linearly independent. That means you take any finite subset, CIPI equal to 0, that can only be true, equal to 0, if all the coefficients are equal to 0. This is what it means to be linearly independent. Okay, but if this linear combination is equal to 0, when we operate on this guy with A, we pull CI's out, this guy all has to be equal to 0. And we know, I'm sorry. Since Pi is equal to AQI, then CPI will just substitute in AQI. So this guy has to be equal to 0. And that's true, since it's a linear operator, we can pull A outside of this finite sum, and we have A operating on this finite sum is equal to 0. Okay, but this finite sum, we know that's in the range space of A star, which is orthogonal to the null space of A. So this guy is orthogonal to the null space of A. Therefore, the only way if it was in the null space of A, then we could get 0. But since it's in the range space of A star, which is orthogonal to the null space of A, the only thing that contains both of those guys is the 0 vector. So when we say that this is equal to 0, we know that that finite sum has to be equal to 0, which means that Qi's are linearly independent. And therefore the dimensions, we get our dimensional argument that the dimension of the range space of A is less than the dimension of the range space of A star, And if we were to go back and substitute A for A star and A star for A, we'll get the second element, or the second statement, which means that the dimension of the range space of A is equal to the dimension of the range space of A star. Okay, I'm going to stop here to make sure that my video is recording, and then I'll come back and do a second video.